Today, we are strapping in for a deep dive into the surprisingly elegant mathematics and foundational ideas that really make modern deep learning tick.
Yeah, we're going right to the source material here.
Exactly. We want to find the core principles that make it all work. For the longest time, AI was great at things that were hard for us, but, well, straightforward for a computer.
Things you could describe with formal rules.
Right, like complex math or playing chess. But the real bottleneck, the real challenge was solving tasks that are just easy for people.
The intuitive things.
Recognizing a face, understanding speech, even just tying a shoe. Formal programming rules just completely fell apart there.
Precisely. Those early AI systems really struggled with the sheer ambiguity of the real world. So deep learning solution was to focus on something called representation learning.
Okay, what is that?
It's about teaching the computer to build complex, abstract concepts, but out of a huge hierarchy of simpler things it's already learned.
So what does that hierarchy actually look like in practice? How do we get from pixels to, say, the idea of a person?
Well, it's very visual. It's meant to mirror, in a very simplified way, how our own brains might work. The goal is to find what some people call a grandmother cell.
A grandmother cell.
Yeah, it's this theoretical neuron that fires only when it sees a specific complex concept, like your grandmother, and it doesn't matter what the angle is or the lighting or how close up you are.
Like it's invariant.
Exactly. And to get there, the system starts simple. It first learns to see basic things like edges and corners, then it combines those into contours and shapes, then those become eyes and noses, and finally, all of that gets assembled into the full, complex representation of a person.
So that's the mission, building this invariant hierarchical representation. And our goal today is to give you a shortcut to understanding the 3 historical waves that brought us here, plus the key math and structures needed to make it all actually function. Let's start with that history, because deep learning didn't just appear out of nowhere. It began as artificial neural networks, or ANNs.
Right, with that explicit inspiration from the biological brain.
Yeah.
And the development really flows in 3 distinct eras.
The 3 waves.
The first wave, this was from the 1940s to the 1960s, was known as cybernetics. The focus was on really simple linear models. It started with the McCulloch-Pitts neuron back in 1943.
Okay.
But the critical milestone, the real game changer, was the perceptron in 1958. This was the first model that could actually learn how to categorize things just from seeing examples.
So before that, you had to program the rules in by hand.
You had to manually set everything. The perceptron learned the weights on its own.
So if the perceptron was so promising, why did the field hit that, that infamous AI winter right after? What was the big flaw?
That is a great question. The perceptron had one massive limitation. It could only solve problems that were linearly separable.
Meaning
You could draw a single straight line to separate the different categories. It couldn't figure out something as simple as the XOR function,
right.
which, well, it requires a non-linear boundary.
And that's what Minsky and Paper pointed out, right?
Exactly. Their 1969 book highlighted that limitation, and research funding just evaporated.
So that brings us to the second wave then. Roughly 1980 to 1995, which they called connectionism. What was the breakthrough that got things moving again?
The breakthrough was all about making depth practical. It wasn't really the invention of the chain rule that already existed. It was the efficient application and, the popularization of the backpropagation algorithm.
Rumelhart and his colleagues in '86.
That's the one. It was the first really efficient way to send the error signal from the output all the way back through the network across 1 or 2 hidden layers. It finally let us train networks to solve those complex nonlinear problems.
And that takes us to today, the third wave, starting around 2006, which is what we now call deep learning.
Yeah, and the catalyst here was Geoffrey Hinton's 2006 work on training something called a deep belief network.
Yeah.
He introduced this brilliant strategy called greedy layer-wise pre-training.
Okay, break that down for us.
The idea is you can't build the second story of a house until the first floor's foundation is solid, right?
Right.
So Hinton figured out how to train the lowest layers first, one at a time, to create a solid set of initial features, and only then did he link them all together. This just shattered the old optimization problems. And the term deep learning really took off to emphasize that we could now train networks that were structurally much, much deeper than ever before.
Okay, so now we have the architecture. But to really get how these things work, we need the toolkit. The source material is very clear that you absolutely need a grasp of linear algebra and probability theory.
You really do.
Let's start with linear algebra.
Linear algebra is basically the language of computation for these models. When you see a matrix vector product, like X beta, you're not just doing multiplication.
Right.
You're defining how an input vector gets transformed.
Yeah.
That matrix beta holds all the learned weights of the model.
So when my GPU is churning away on a deep network, is it basically just doing billions of these matrix multiplications at incredible speeds?
You nailed it. That's where almost all the computational cost is. And a really critical concept there is the span of a matrix.
Why does the span matter?
Because the span defines the entire set of all possible outputs you can get from that transformation. For a neural network layer, it's the range of features that layer can possibly represent. If your data needs something outside that span, well, the layer just can't do it.
And some matrices are better than others for this?
For efficiency, absolutely. We love things like diagonal matrices. They're almost all zeros, so multiplying by them is incredibly fast, and inverting them is trivial. Finding ways to use structures like that can make algorithms much, much cheaper to run.
Okay, that's the computation part. Let's pivot to the second piece. Probability theory. This is all about reasoning under uncertainty.
Exactly. And what's fascinating is that AI uses two different philosophical views of probability. The first is the one we all learn in school, the frequentist view.
Like flipping a coin or drawing cards.
Right, rates at which repeatable events happen. But the second view, and this is often more important for AI, is the degree of belief view. This is for things that are not repeatable.
Like what?
Like a doctor saying a patient has a 40% chance of having the flu. It's not about repeating an event. It's about the model's confidence in one specific, uncertain proposition.
So how do we describe these probabilities mathematically? I see PMF and PDF mentioned a lot.
Simple distinction. The probability mass function, or PMF, is for discrete things, like the outcome of a die roll. The probability density function, or PDF, is for continuous things, like a person's height.
Got it. So we've got our linear algebra for the how and probability for the what if. Now we can get to the central challenge of all machine learning, generalization.
Yes, performing well on data you've never seen before.
And good performance depends on two things, right?
A delicate balance.
Yeah.
First, you need a small error on your training data. But second, and this is the hard part, you need a small gap between that training error and your test error.
Which brings us to this key idea of capacity, a model's ability to fit a function.
Right, and it's a spectrum. If your capacity is too low, you get underfitting. The model is just too simple.
Like trying to draw a detailed portrait with just a stick figure.
Perfect analogy. Both your training error and your real-world error will be high. But if the capacity is too high, you swing to the other extreme, overfitting.
This is where the model basically just memorizes the training data, noise and all.
Exactly. It gets so focused on every tiny freckle and stray hair in the training photos that it fails to recognize the same person in a new photo. Your training error might be 0, but your generalization error goes through the roof.
So how do we control this? How do we find the sweet spot?
This is where regularization comes in. It's basically about building preferences into the learning algorithm to guide it. You can think of it as the machine learning version of Occam's razor.
Pushing it towards simpler solutions.
Exactly. For example, L2 regularization, or weight decay, just encourages all the weights to be small. But something like L1 regularization is different. It encourages the weights of unimportant features to go to exactly 0.
Oh, so it's doing feature selection for you.
It's doing feature selection automatically. It makes the model sparser and often easier to interpret.
But hold on, if we're building our own preferences in, aren't we just baking in our own biases? How is that objective?
That's a fantastic point, and it gets to a deep truth in the field, something called the no free lunch theorem.
Okay.
It basically says there is no single best machine learning algorithm. If you average performance across every possible problem in the universe, every algorithm is equally good.
So the choice has to be specific to the task.
It has to be. You must encode prior beliefs that align with the specific problem you're trying to solve.
And we make those choices using hyperparameters, things like the learning rate or those regularization strengths we just talked about. How do we tune those without cheating and looking at our final test set?
You need a firewall. You create a dedicated validation set, you carve off, say, 20% of your training data, and you use it only to tune those hyperparameters. You train the main model parameters on the bigger chunk, then check the performance on the validation set to tweak the hyperparameters. Only when you're completely done, lock everything down, do you finally run the model one time on the unseen test set to get your true, unbiased score.
Okay, let's put it all together now in the main architecture. The feed-forward deep network, or multilayer perceptron, the MLP.
The quintessential model. The depth comes from that chain of intermediate or hidden layers. The key is that the training data never tells the model what to do with those layers.
The algorithm has to figure it out on its own.
It has to learn how to use those layers to structure the data and build that hierarchy we talked about.
And we know we need depth and nonlinearity to solve things like the XOR problem.
Absolutely. And the modern default for that nonlinearity is the rectified linear unit, or ReLU.
It sounds fancy, but the math is super simple, right?
It's just GOZ. It chops off anything negative and lets positive values pass through unchanged.
So why does this one simple function dominate the entire field?
Because it just works so well in practice. For all the positive inputs, its derivative is exactly 1. It's almost linear, which makes gradient-based optimization much, much faster and more stable. It helps avoid the vanishing gradient problem that plagued older functions.
But wait, there's the universal approximation theorem. It says that just one hidden layer is theoretically enough to represent any function. So why are we building networks with dozens or hundreds of layers? Isn't that just a huge headache?
It's a great challenge. And yes, in theory, one layer is enough, but it might require an exponentially huge number of units to do it, just impossibly wide.
Ah, I see.
A deep network can often represent the same complex function with exponentially fewer total units. It's far more parameter efficient. And that smaller model size often leads to better generalization.
Because it reflects our belief that the world is compositional.
Precisely. It's a structural prior that helps the model learn better.
Okay, so the complexity is worth it. But the actual process of training these deep non-convex models must be a nightmare.
It is extremely difficult. In these high-dimensional spaces, you don't really run into local minima that much. The bigger problem is saddle points.
Remind us what a saddle point is.
Imagine a horse's saddle. From the front to the back, it curves down. But from side to side, it curves up.
So it's a minimum in one direction, but a maximum in another.
Exactly. And at that point, the gradient is almost zero. So the optimizer just gets stuck on this huge, flat plateau and can't figure out which way to go. It wastes enormous amounts of time.
So what's the modern fix? How do we navigate these horrible landscapes?
Well, stochastic gradient descent, SGD, usually with momentum, is still the foundation. But for truly deep networks, a technique like batch normalization is basically indispensable.
Batch norm, I've seen that everywhere. What's it actually doing?
It's a clever trick. It reparametrizes the layers to keep the mean and variance of the internal activations standardized throughout the network as it trains.
That sounds like a small technical tweak, but you're saying it's a huge deal.
It has a massive impact. It dramatically reduces the problem of coordinating updates across all these different layers. And the biggest win is that it lets you use much, much higher learning rates, which means the network trains way faster. It just stabilizes the whole process.
What a journey. I mean, from the simple linear perceptron through the key idea of backpropagation and now to these massive deep networks that are only made possible by clever math, like ReLU and optimization tricks like batch normalization.
And that ability to manage the optimization is what finally delivered on that original promise of learning a deep hierarchy of representations.
So to wrap this all up, what's the big takeaway for you? Where does this leave us? I'd like to leave you with a final provocative thought from the source material.
Go for it.
It's that the success of deep learning has actually outpaced our ability to measure it. The field today struggles mightily with evaluation, not just with building new models. The metrics we use to see if a model is any good often have serious weaknesses. This means that designing new, better ways to evaluate them, to know if a model truly understands something or if it just got good at pattern matching on the test set, is one of the most important and active research topics in the entire field today.
We can build them, but we're still figuring out how to be sure we know what they know.
Exactly. Thank you for joining us for this deep dive.